So let's solve one problem here. So here we have an impulse turbine of 1 megawatt has steam entering at 20 bar and 300 degrees Celsius and steam consumption of 8 kilograms per kilowatt hour because this nozzle is installed at the start of an impulse turbine. Okay, which we'll see in the next impulse turbine, and that is its total power output of the turbine. So at the inlet of the turbine, there is a nozzle. At the inlet nozzle, so now here we have nozzle, then we have that turbine like this. Here, this is our system. Fluid is entering here at T1 point 300 degrees Celsius. And the steam consumption and the power output of that turbine is given 1 megawatt. And steam consumption of 8 kilograms per kilowatt hour. So where steam consumption is given something 8 kilograms per kilowatt hour. The amount of steam which is flowing to produce 1 kilowatt hour is 8 kilograms. Steam leaves at 0.2 bars and 10% of the total heat drop. Now steam leaves where? Actually, we will see in the next chapter that for impulse turbine, all of this pressure drops inside the nozzle. Okay. Pressure drop over this turbine is negligible. There is a pressure drop due to friction. That is what is happening in an impulse turbine, but in reaction turbine, it is not like this. Some pressure drops in the nozzle, some pressure drops in the turbine blade because their turbine blades are also nozzles here. But here in the impulse turbine, it's not like this. So here, steam leaves at 0.2 bars. Actually, it is leaving the nozzle at 0.2 bar. But here also, if we neglect frictional losses, so it will be leaving at 0.2 bar also from this turbine. And 10% of the total heat drop. Total heat drop means delta H, U plus PV. 10% of the total heat drop is lost in overcoming friction in the diverging portion of the nozzle. So, in other words, 10% is frictional losses. It means nozzle efficiency is 90%. That's what it's. And that is only for the divergent part. Okay. So it means from inlet till throat means C. The process is isentropic. But from C to 2, it is non-isentropic. Because this nozzle efficiency is given only for divergent part. If the throat diameter of each nozzle, now each nozzle is 1 centimeter. So the throat diameter of one nozzle is given. So diameter at the throat of each nozzle is 1 centimeter, then determine. So in other words, area of throat is already given. Determine the number of nozzles required. Okay, so now what is meant by number of nozzles? So let me show you one figure where you will understand how exactly this impulse turbine look like. Here you see an impulse turbine mounted over a rotor. Here is that shaft. These are turbine blades. And here you see one, two, three, four nozzles. So the total amount of m dot coming from boiler is then divided into 1, 2, 3, 4 nozzles. So the whole of the steam is supplied over the whole rotor at 4 different points. That is what we need to find out in this question. For this condition or for this situation, the total number of nozzles required, we need to find out. As an example, 4 are shown, but we do not know how. So that's what we need to calculate. So this is our problem. So first, what we can do here, the total mass flow rate is given to produce 1 kilowatt hour. So it means we can find out the total mass to produce 1 megawatt. This is for 1 kilowatt hour. So we can find out the total mass flowing for 1 megawatt hour. See how much mass is flowing through this one nozzle. Yeah. After accounting for all those losses, whatever. We do not know what is the history behind this that is given in this question. So it means we need to find out the mass flow rate through this one nozzle whose throat area is given, and then see how many nozzles would be required. That is the question. So it means first we need to find out the mass flow rate through that one particular nozzle. So how to find out the mass flow rate? Mass flow rate is decided by area of throat. So ACCC over. So let's find out this mass flow rate. Area is given, CC we can find out. 2 into H1 minus H. Okay. VC we will find out from tables. H1, HC from HS chart of table. That is VC from tables, because in charts we do not have volume lines. There are charts having volume lines, but who will read it? So that's why we have to use the table here. So you can see HS chart in Sengel's book. HS chart is there with volume lines. So if you open it, you will see it's too much closer to each other. Very difficult. You will need a magnifier to read it. That's so that's the question. So the first part is clear, and then we need to find out the exit diameter of each nozzle first, and then find out exit diameter. Solve using Mollier diagram. This HS chart is called Mollier diagram. Here is the HS chart. Okay. Of course, at the start, we do not know where is point C, where is point 2, but of course he knows. That's why it is mentioned C is in still superheated region, point 2 is in mixture region. Okay. So this is the equation to find out mass flow rate. But to find out the enthalpies and VC, we need PC, critical pressure. And we already know this simple equation which we derived. And till throughout, it's isentropic. And this equation was for isentropic also. Okay. So find out. Gamma is first you have to check this point 1. If it is superheated, then gamma is 1.3 for superheated steam. So find out PC, that comes out to be 10.9 bars. Critical pressure. And that is because here it's not mentioned, it is convergent divergent nozzle. But now you can tell because here is PC, what is P2? Lower than this. So it is a convergent divergent nozzle. That's why it is written, it's a convergent divergent nozzle. Here it was not mentioned what type of nozzle. It could be a convergent nozzle. Okay. If PC comes out to be equal to 0.2. Then let's now find out CC, H1, and HC because now PC is given. So all these values from this chart, H1, I think it is 300 degrees Celsius. Whatever is the pressure, right? 20 bars was the pressure. So where is the enthalpy? For the same line, the second pressure, we calculated 10.9 something. So this is point 1, this is point C, 10.9 something. So this is 10 bar. So here, 11 bar, because this is 15, this is 20. So roundabout here. So this is HC. This is H1. So directly from that table. H1, HC multiplied by 10 to the power 3. So that is CC. That is the sonic velocity of the steam at this pressure and temperature, 10.9 bars, and whatever was the temperature here. Okay. We can also find out from gamma or T critical. There will be some error because here that is ideal gas equation mainly. So, but anyways, so this is CC, sonic velocity. It's very high, 532.9 meter per second. It's very, very high velocity. If you convert it in kilometers per hour means divided by 1,000 multiplied by 3,600. Because why kilometer per hour? Because we drive cars, so no, we can imagine what is meant by kilometer per hour. So let's see how much it is. 532. 9 multiplied by 3,600 divided by 1,000. 1918. Can you imagine the speed of that steam? You cannot even imagine. And that is the sonic for steam. And so it is convergent divergent. So it means velocity at exit will be even much higher than this one. So this is the velocity at which this steam is moving. So now you can see the role of nozzle here. Without the nozzle, no power. Nozzle is so important. Okay, nozzle is the one which is converting this pressure into velocity, kinetic energy. Otherwise, here are the tables. See the tables. And because now in any case for VC, for specific volume in this equation, we have to use table. So VC, so now at 10.9 bars, but in the table we have, this is 10 bar, 1 megapascal, or 12 bar. So we do not have 10.9 bars. So, and entropy is, we can also see entropy from the same HS chart, about 6.78. Yes. 6.75, whatever. So here, 6.78. So now you need to find out 6.78. 6.78 is between this and this. Yeah, different pressure, because pressure is already between this and this. Pressure is also between these two values. Entropy is also between these two values. So that's how we have to find out this volume. Look, the change in volume is already very, very small, 0.192, 0.2. So for the exam, just take the average. Otherwise, how to do interpolation? What is to be find out volume at 10.9 bar? That is unknown. Minus 0.20602 divided by 0.20602 minus 0.19241. And what is known? Entropy 6.78 minus this 6.6956 divided by 6.8313 minus 6.6956.
The specific volume and 1.2 at this entropy at the turbulent speed and also the 1 megapascal.
Then take the average.
We do also interpolation for the pressure. So for the interpolation. That's what we.
Yeah, maybe. So when I did like this, so I got very similar answer as in the, but that one, because with the different pick, that's one. Anyway, so this is VC 0.2. So whatever you like, because in this course for exams, I'm not asking you to, but you should know this. You should know the way. Otherwise, nowadays, uh, tables, formulas are available in apps and programs. Just put the value and you will find out for a given pressure and temperature. So this is specific one. So now we know specific volume. CC, AC is already known, so we can find out mass flow rate. See, mass flow rate. Put all the values here, 5 by 4 d square area. Okay, this is for converting it to meter. I think centimeter is given. Yes, centimeter is given. This is the mass flow rate, kilograms per second. For one nozzle. Now we need to find out the total number of nozzles. So here, let's try to understand that is the total amount of mass which is required to flow, but for how much kilowatt? 1 kilowatt hour. And how much is the power required? 1 megawatt, 1000 kilowatt. So this is the flow rate for 1 kilowatt hour. And this is the total hour, sorry, the total power which is required. So it means this is the mass flow rate for 1 kilowatt. And there is hour, so convert this hour into seconds. 3600 seconds per hour. And this is the mass flow rate from one nozzle. So this term is actually representing the total mass flow rate divided by from one nozzle. But you have to bring all the units to one. Actually, all units should cancel because here we are trying to find out number of nozzles. So you see this kilowatt will cancel with this watt, this hour cancel with this one, second cancel with this one, kilogram cancel with this one. So it becomes unitless. Okay. So here there is no formula. Here just you need to play with the units. Out of just simple or basic understanding of the terms, what this term is representing, what this term is representing, and divided by this. So this will give us the total number of nozzles for this turbine. So it comes out to be 10.63, so 11 nozzles. So this total mass flow rate will be divided into 11 nozzles equally placed over the whole circumference. Okay. Yeah, it should be symmetric. Otherwise, there will be rotor will be vibrating. So what should be the diameter and all these things we'll learn in the next chapter. What should be the height of the blade? So those things are the next chapter. So any questions? So this was part one to find out the total number of nozzles. Next is to find out the exit diameter because pressure is not dropped till 0.2. It was dropped up to 10.9. So it's not a convergent nozzle, it's convergent divergent. As you see also here, entrance, here is throat, and here is divergent part. If you see this nozzle, the steam coming from boiler. Okay, so exit area is similarly same m dot A2 C2 over V2. So find out C2. So now it will be 2 into H1 minus H2 from 1 till 2. And here nozzle efficiency is given. So yes, you can do from HC also. You will write HC minus H2. Yep.
Just will be different answer.
Yeah, I'm thinking. Yes. Here what we so at CC. This was under root till here. Yes. No, till here. We were neglecting C1, but now see if you write it from so CC cannot be neglected. So this should give us the same answer.
C.
HC minus H2 plus C1 square, which will be CC square, because now
Sandal was correct.
I think it was a outside under root. Inside? Yes, inside. Inside. Okay. So then this will be the equation. Yeah, try it home. Let's see what. Otherwise, just keep it simple. H1 minus H2, C1 is negligible. So here we need to find out H2. How?
Condition by the emissions.
But H2S.
Uh,
So here is the lowest pressure, 0.2 bar, I think. 0.2. So this is H2S. Efficiency. Pressure is given, and it is inside the dome already. Okay. So find out H1 minus H2 over H1 minus H2S. This is given as 0.9, so H2S, H1, all given, so find out H2. Okay, where we are. So this is H2S. So here is H2. Look, H2 is higher than H2S because enthalpy drop now in actual case is lower. H1 minus H2 is smaller than H1 minus H2S. That's why velocity rise will be less or kinetic energy rise will be less. Okay, then C2. 2 into H1 minus H2, just put values. So here is C2. 1196 meter per second. How much was CC? 500. Oh my God. This is the velocity with which the steam is moving. That's why they use number of nozzles. If only one nozzle, your turbine will definitely break. So not this power which we are using, how it is produced. Look, only 1 megawatt we are talking about. Okay. So it's not just the fuel. After that, so many things are happening, which is giving us this power, which we use so cruelly. Switch on, everything is on. So far, 80% around the world is coming from these turbines. At least more than 50% is still coming from, is being produced from these turbines. Only 1 megawatt, and look at the.
Actually, pressure drops, enthalpy drops because of nozzles. There are to kinetic energy, and turbine turns that kinetic energy
Into power, rotational power. So pressure is actually dropped in nozzle,
not in turbine.
not in the turbine. For this impulse turbine, there is another type reaction. Reaction turbine, those blades, they are nozzle shaped. So we'll see in the next chapter. That's why next chapter will be very interesting. Yeah.
The pressure.
Yeah.
Not the turbine. So our whole life was a flight.
Yeah, because in so far we in Thermo 1 or 2 we were just showing this thing and we were saying it's all pressure drop here. Actually, inside that box there is this important thing which is doing this task actually. Okay, that's why I used to tell you that when we will open this box, there is a whole new world you will see, and that's what you are seeing now. Okay. It's not only in steam turbines, also in hydraulic turbines. Civil engineers, not only the hydraulic turbines. It is first is from high to low height potential energy is converted into kinetic energy. Then it is passed through a nozzle, and then it is tracking that hydraulic turbine. Again, there is also a nozzle. All right. Okay, now V2. For V2, now there is that way which you already know, V2F flux X2 V2FG. But what about X2? We can find out X2 for this point. What about this point? Yes, H2 is given. Find out X2 from here and use it here to find out V2. That's what we already know. Or find this, we can locate this point H2 in HS chart because now enthalpy is calculated. So go to the chart. Enthalpy is, we have just calculated. Same pressure, 0.2 bar. So it means this point is H2. Corresponding to this point, here is the quality line. So directly read quality line from here.
I think we can directly view it from table.
X2.
How much to?
Now I need X2 to find out V2.
I know how much to.
You know H2, okay. From that you will find, yes, by from that equation. But if you do not want to use that equation, you want to save your time in the exam. So here is H2, read X2 directly. That's what I'm saying. That's what you already know from thermo basic. But if I can write, because now we know H2. So draw a line. This is H2 line. Here is the same pressure, 0.2 bar. So here is the point. This is 2S. Now this is 2. This is 0.2. And read quality. So what is quality now? Here it is 0.9, 0.85, so 0.87. 0.87. So whatever you want, you can use it, of course. Whatever way you like. Now, there is no escape button. Yes. Escape. Okay. So this will give us X2, and from X2 I can find out now. V2 in any case you have to, because volume lines are not there. If volume lines, if you can bring a chart of your own with volume lines, share with me. I will share this one. So no need to calculate even volume also. Because this is already, you did it in thermo 1, thermo 2, so you know the procedure. So here is that volume, so just put, so here is the area, required area of one nozzle at exit to have so that supersonic velocity. So here we are calculating area to reach that pressure without any shock. Yes, I wanted to show you those equations last time.
Make sure that there is no shock here.
Because we are keeping that 0.2 bar at the exit, and we have calculated this area based on this 0.2 bar. That's why. Because 0.2 bar and 20 bar is in our control. That's why. If something is not in our control, then yes, there is always a possibility, like the jet engine going into the space continuously. The exit pressure is changing there, yes. Yeah, but
how, okay, I understand how you're controlling the area and the intake pressure, so the inlet pressure.
inlet pressure is a boiler, which we are designing. Exit pressure is condenser. After turbine, what is the next component? After turbine, condenser. So condenser, in the condenser, you have that vacuum pump which is creating that pressure. So between boiler and condenser, that is these are the two pressures we are controlling. In between, we have this nozzle and turbine. So that's okay. Last time I just wanted to show you one equation here to have shock-free flow through a nozzle. There is one equation which you can find out in aerodynamics books, not in this book here. Here is that equation. Uh, whatever mass Mach number we want, we can find out this area ratio. This is an equation. Whatever supersonic mass flow rate we want. Okay. And corresponding to this one, what should be the pressure ratio? This is the equation. Okay. So for the same Mach number, this should be the pressure ratio from inlet to exit to have shock free. So from here, we can find out the area for to achieve that Mach number. But in parallel or simultaneously, this should be the pressure ratio to have shockless flow. So these equations have been derived, not here, in some other books, which we can see.
So the first one is the area for non-shock internal.
Areas. No. The first one is telling us the areas to achieve that Mach number. To achieve that. Now, this Mach number is known. What should be the pressure ratio? To not have pressure ratio. So one of the pressure is given, so what should be the other one? Okay. Or the exit pressure is given, what should be the inlet one to have smooth flow? So that is
First
area
for
to reach that Mach number, whatever we want. Second one,
shock
pressure
for no distance.
for no
For
shock. Yes, exactly. Okay, just for your info, it's not a part of your course. Of course. Okay, so now the next topic, which is also very interesting, supersaturation. So this is a phenomena which occurs only in steam nozzles, not in gas nozzles, only in steam nozzles. So steam, this is the steam coming from, for example, boiler, and here it is going to the condenser. Okay. So here in this process, which is shown 1 to 2, there is in between a point A where what is happening? Yeah, transition from superheated to saturated. And after that, A to 2, 1 to A is all superheated, and A to 2 is in mixture. That's what we think it will be like this. But for the fluid which is flowing through that nozzle, and we just saw the velocities. 2000 kilometers per hour plus 3000, 4000 kilometers per hour. At such high velocity, condensation does not occur at point A. They forget to condense. They don't have enough time to condense. Here, the condensation which we see here, this air is flowing in this air, there is moisture. They have enough time to condense. exactly at that point where this curve is showing us, but not in nozzle. That's a unique phenomenon. About 1 to 2 centuries before scientists they observed this. Only for steam, when the steam nozzles and these turbines started to appear first. So, and later on, the other scientists and researchers, they confirmed this thing experimentally. And, and this is now established fact. That happens whenever the fluid is flowing through a nozzle at such high speed, it does not condense at point A. Condensation is delayed. For how long it is delayed? No, no. It until this pressure and temperature drops to a line of X about 0.96. Does not one. It is delayed not by time or by other things. This X, just imagine this curve is shifted. This X is equal to one curve is now as X is equal to 0.96. At this point, whatever is the velocity, it will condense immediately with the shock. It is called condensation shock.
We don't have directly liquid mixture.
Mixture, yeah. But now what they observed, it remains gas till this point until X approaches about 0.9596. Then there will be a condensation, a sudden condensation. Before it was a gradual condensation. So now it will be a sudden condensation to 0.96 value or 0.9. Suddenly you have more water. Because velocity was so high, the molecule, because for condensation, so many cluster of molecules should join together to make liquid, which was not possible at this high velocity. So it is delayed, but it is not delayed for indefinite. There is that line, that imaginary line is called Wilson line. They name a person Wilson line, at which this condensation will occur. Okay, so far things looks very easy, but now there are some complexities which we'll try to understand. Okay, so
Only for steam
only for steam.
doesn't make sense.
Why? For other fluids we do not use normally at such high velocities. Which fluid we normally, maybe in some other application it also occurs. Steam nozzles and steam turbines, that's what people are using all over the world. But at the same speed, if for some other vapor, for gases, it doesn't, there is no issue, such thing. Gases we are using at such high velocities, but there is no such thing, supersaturation. They, of course, they are far away from condensation point. But maybe the same thing happens for those gases if if we are performing this task near to their dome. But to reach their dome, now you can imagine the temperature which you have to probe. So that's why, for steam, that's why it is definitely occurring. Or we can say with surety for steam. Okay. Because every substance is different from each other. Its molecular nature. Maybe it will not occur exactly in the same manner as for steam. Okay. So that's what is written here. Whenever superheated vapor expands isentropically, condensation within the vapor begins to form when the normal phenomena, when the vapor line is reached, saturated vapor. So point A represents the point at which condensation within the vapor just begins. That's what we know. And that is shown on TS diagram. The same is shown on HS diagram. Okay. It is found that the expansion through a nozzle takes place so quickly that condensation within the vapor does not occur. Vapor continue to expand as superheated vapor until some point at which condensation suddenly occurs and irreversibly. That is named as condensation shock. Point at which condensation occurs may be within the nozzle, somewhere here. This point is reached, this phenomena is occurring, or maybe out right at exit, or maybe after it leaves the nozzle. Okay. Yeah, that depends, whatever is the condition. Okay. So this expansion of steam, we call this expansion with supersaturation phenomena metastable equilibrium. Normally we say equilibrium, it's throughout equilibrium expansion, but this type of expansion with delayed condensation, it is called metastable equilibrium because the change of steam state could not maintain its pace with expanding steam. Change in state delayed, right? So how much it is delayed, I already explained it to you. So it will condense at this point somewhere at x is equal to 0.96. And that may be within the nozzle this point, or that may be outside or right at exit of nozzle. Okay. So because for condensation, you need some residence time, some time to rest for those fluid particles. And also, but this time is not available when the fluid is flowing at such high speed. So that's why the condensation delayed. So this phenomena in which change of steam state could not occur simultaneously with expanding steam in a nozzle. That type of flow is called supersaturated flow or metastable flow. There are two names. It should have been saturated here, but that as this point is shifted here, so this is called supersaturated. Okay. Yeah, about this one.
Does that make difference?
Hmm?
Does that make difference?
Does that make difference to what?
And
Yeah, we'll see. No. Okay. So once the temperature, okay, all this we have discussed. Wilson sign is that locus of all those points where condensation takes place immediately. And it is not dependent upon point one. Wherever is the point one, here, 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 or here, condensation will take place at about this x.
for any years,
For any,
doesn't
no, until it is, no, not until it is supersonic, whatever is point one, right? Whatever is point one. But if you are in the sonic to supersonic range, this occurs. Okay. So you can have supersonic with this point one, with this point one, maybe with this point one, with this point, whatever is the inlet point, but condensation will finally occur when x is about 0.96. X line of 0.96 reaches. Okay. So this Wilson line lies between 4 and 5% moisture curves on this HS chart for steam. Okay. So this theory we have understood, we have covered. Now let's further discuss it in more detail. First, see on TS diagram. Okay, condensation should have occurred at point A, but it doesn't not, it did not. It was delayed till point R. For example, this point R is representing x is equal to. Okay. It means for this supersaturated flow, this portion A to R is also superheated for this flow. If it is also superheated, then this pressure line on TS diagram will continue like this as in superheated region.
Why?
Because this line x is equal to 1 line is shifted here. This is new x is equal to 1 line, which is actually x is equal to 0.96. Actually, it is 0.96. But for this fluid, it is x is equal to 1 till. So it means this pressure line, which changes its slope for normal flow, it will not change its flow. It will continue like this. So that pressure line is extended till point R. So here you see point R temperature is lower than point 2. This is called degree of supersaturation. Actually, point 2 is corresponding to P2 in normal condition. But now this point 2 is shifted to point R. And point R is lower than point 2, normal point 2. So this TR minus T2 is called degree of supersaturation. Okay. If we show the same thing on HS chart, okay, this is clear. This is called degree of supercooling. Sorry, not supersaturation. T2 minus TR, degree of supercooling. Now the same is shown on HS chart. Now on HS chart, the same R point is above point 2. Same process is shown HS chart. But now point R is above point 2. Why? Answer is not in the book. And yeah, once I taught this for very first time, I thought a very long. Why? Why?
Yes, sir.
Then I made a separate slide to explain this thing, the next which I will show, only to explain this thing. Why? Point R is above point 2 on HS chart. On TS chart, point R is lower than point 2.
R represents the new.
Yes.
Uh,
Okay, so let me say this new saturation curve. So this is shifted here. Okay. So the same thing which we were saying there in TS diagram for pressure line, same now we have to say for HS chart. On HS charts, normally we saw those pressure lines, they are like this. Okay. Sorry, actually they are like this. You have to see very closely. From here to here, this pressure line shifts a bit here, not here. Yeah, it is going like this, and there is a little shift. Just like here the shift is very much clear. It was inclined, then it becomes exactly horizontal. Here, if there is no saturation curve, this pressure line will continue like this. It's down in actual HS chart after saturation curve is extended further. So now here in this case, point R is above point 2. Okay, now the question is, here we said TR is less than T2. Can we say the same here? Yes, we should. So it's clear.
No, sorry.
It's not clear, but it should be the same. Clear?
He's saying R is having more current.
Yeah, that is another thing which we observe, which we cannot observe on TS chart. But here we can observe that H1 minus HR is lower than H1 minus H2. That is more relevant to nozzle. That now with supersaturated flow, enthalpy drop is less. HS chart is telling us. So it means the velocity will be a little less than what we are thinking.
Direct line, Peter, for Peter. Okay? Which one is the actual one?
For supersaturated flow, actual line is dotted. For normal flow, it is 0.2. Now we need to understand this thing.
What's the dotted line?
YTR. Dotted line is the pressure line. If I say this this saturated curve is shifted here. So this pressure line would have been continued like this. So point R will be on that imaginary P2 line, right? And that's what we observe. Another thing, we observe this thing from TS diagram, we observe this thing from HS chart, but this thing, is it same here also? That's what we need to understand. Okay. So that's why we have to see temperature lines. That's why I made another slide separate to explain this. And then we will come to understand what is happening to volume also. That will be done later on PV diagram. Okay, now let's see. This is T2 line on HS chart, temperature line, and it will be this one inside the dome. Inside the dome, both temperature and pressure are same. Just like here on TS diagram. Okay. R line means now this saturated curve is shifted here. So it means there is a temperature corresponding to, there is another temperature line. For a normal flow, it would have gone like this. But now because this is shifted, dome is shifted here, so this TR will continue till this point R. Now TR is, now you can imagine TR is less than 2 because dome is shifted to point R. So this TR line will continue its curvature till, so now it's clear. Okay. Clear? Why TR is less than T2. So that's what I wrote it here. Because once I understood, I was jumping. Oh, I understood why. Then I made this graph for students. Okay, so that no. Now what is left? Now let's see volume. Volume here it is saying VR is less than V2. If you are very super genius students, now tell me why. V2. How?
Physically or from charts?
For supersaturated flow versus normal flow, it is saying that VR,
Okay.
when there is supersaturation, it will be less than when there is normal. That's what we said for TR and T2. For a normal flow, what will be T2? And for supersaturated flow, TR is now less than T2. The same is for VR. VR is less than V2. You can answer this thing only with the help of this. If you remember this diagram from Thermo. Yeah.
Okay. Bro.
Okay, it's being recorded, so I cannot wait. Okay, let me show you. Okay, we will come back to this one later on. Let's see here, this PR. What is this PR line? Look, corresponding to this, now we know what is TR. So this TR, if it is a normal flow, then TR would have been like this. So it means corresponding to this TR, there is one PR. So it means PR is less than P2. PR is a normal pressure we are imagining for that point R. Actually, point R is here, but I'm saying for this this TR, which is lower than T2. If it is a normal flow, then TR corresponding to this TR, this would have been PR. Okay, so here we are defining one more thing, which we call as, one was degree of super cooling, another is degree of supersaturation. T2 over PR. What is PR? PR is corresponding to that TR. But that TR, if we imagine it to be going like this, so normal condition. So this P2 over this PR is called degree of supersaturation. So there are two terms, degree of supercooling. Second is degree of supersaturation. Okay.
One is subtracting and one is ratio.
Just to define this definition, they are using this PR concept. Okay, nothing else. Okay, so that is clear. Now enthalpy is clear. Now for supersaturated flow, now we'll discuss volume later on, maybe in the tutorial class. Okay. And enthalpy drop in supersaturated flow is less than the enthalpy drop for equilibrium. So this flow 1 to 2, we are calling it equilibrium flow, and 1 to R, we are calling it supersaturated flow. Okay. So if you compare the equilibrium flow with supersaturated flow, the enthalpy drop in supersaturated flow is lower than normal equilibrium flow. So this will mean that exit velocity of supersaturated flow is less than that of equilibrium flow. That is important from nozzle point of view. But from nozzle point of view, there is one more thing important, m dot, because m dot is equal to AC over V. So we just saw that velocity is drop. Now we'll see for specific volume. So we'll see that specific volume also drops. Then we have to see which one is more, whose effect is more dominant. Because this drop will make the mass flow rate drop. This drop will make the mass flow rate to rise. So then which one is more dominant? That will define what happens to this mass flow rate. And this we will discuss, you will know this is more dominant. So mass flow rate through a supersaturated nozzle drops compared to normal flow. That's what they observed first. Then they start digging up why. For steam nozzles, they observed that mass flow rate is lower than what they theoretically expected. Okay. Not a huge value, but there is some lower m dot, because this m dot is defining our power output of turbine. This m dot, which is developed. Okay. Okay, so just look at this, and then we'll have some more interesting things about this supersaturated flow, so which we'll discuss there later on. So I will discuss this thing. Until then, you can understand by yourself why VR is. Hmm? So we'll see. Answer is here. You will find the answer here on this slide.